This trapezoidal section is maintained throughout the length. Okay, so this line is straight, or it can be a little curved depending upon the route of this canal that we decide, but generally it is kept straight in this fashion. So the water will be flowing in this way. Okay, so water will be flowing in this way. So this portion is called freeboard. This is the maximum water level that we can release into the canal, and the bank is a little above that. So this depth is called freeboard. But when the water has entered into the canal along with the suspended silt, can we remove this silt also? So the answer is the next structure, that is structure 2. So how that structure acts, how that structure performs this task of removing the silt from this water which has already entered into the canal. The silt which has already entered into this canal along with this water, how to remove it. Okay. For this, let us see, this is the top view of the canal. Okay. This is the bed width. This is one side slope. This is other side slope. And on the adjoining area shown as green, this is the natural ground level. So this is the excavated portion of the river. Oh, sorry, canal. If this is the canal, let us say that water is coming from left hand side and it is going to the right hand side. So we will be having a head regulator on this left hand side somewhere, and water is moving from left to right. So what we do is we depress the canal bed a little. So this is the depressed horizontal portion. We depress this bed over here. So this level is lower than the canal bed level. Okay. And to join these two levels, we have provided a inclined ramp. So it is not depressed all of a sudden. So from here, it is the canal bed. From here, it starts gradually going downward up to this level, and we maintain a horizontal depressed floor up to this. And this is basically done in concrete to secure this depression of the bed and to secure this ramp also. We provide everything in concrete, with the concrete. Okay, concrete floor is provided in this station. And once we have this, depress this bed also, we cut this one side bank at the same level. So this cut is also provided. So we cut one side of the bank. As of now, there is no water in it. Okay, we cut downstream, one side of the bank. Then we provide a wall of this shape. One thin wall is provided of this shape. Second wall is provided, third wall is provided, fourth wall is provided in this fashion. So they are low height walls, very thin walls, and their top level of these walls is little above the canal bed level. Okay, little above the canal bed level. So what you see is here the gap between the walls is very high. Here the gap between these walls is low. We can provide these intermediate walls also, which may not run up to this end, but they are provided in intermediate position and they run up to these points only, here, here, and here. Okay, so the water which will be going through this, they will be ultimately merging here. So here and here, they will be merging over here. Okay, so they are provided in this fashion. So the height of all these walls, the top level of the wall is at the same level, and that is a little above this canal bed level. Thereafter, we cover it with the concrete slab. Very thin diaphragm slab is provided on the top. It is covered on the top side. But you see here, we have not provided any slab. So the water in the bottom layer has the passage in this portion to move underside of this slab and go into these tunnels. Here also we provide this concrete slab. The yellow lines again indicating the bottom layers with high silt content, they move along the bed, and here you can see they have entered below the diaphragm slab. So this slab, I have made this slab a little transparent so that you can see the these walls also. So where these flow lines are entering, and ultimately they are diverted here and go to the sideways. So the flow of water in the canal is here, but the bottom layers are segregated to move out of this canal. Okay. The top layers, they move to the downstream side just above the diaphragm slab. The top layers, they do not enter into this portion. So top layers move further. So the bottom layers can be separated out and they can be removed out of this canal. Okay. But how much quantity of water can be removed, should be removed? For that, we provide gates over here also. Like 3 gates we have provided for these 3 channels, 3 tunnels. So we can operate these gates and we can control the quantity of water to be released to the outward side. Okay. Now, once we have achieved this, we plug this excavated portion of the bank in this fashion so that now this channel section remains intact again. Only the bottom portion has got some opening where the bottom layers will be entering into this portion and they will be collected through this series of tunnels and they will be taken to the outward direction. So this is called silt ejector. Okay. So this is the second category, silt ejector, and this is the diagram that is available in the books. You can see this is the canal. Here we have the gap. Some diaphragm slab is there. If you see this section AB, it is here. Some diaphragm slab is also provided at section AB. This is the canal bed level. It is depressed a little in this fashion. And in this portion, these walls are provided. So you can see these walls are very sharp. They are offering the bell mouth entry into the every tunnel, and ultimately the water is collected and ultimately released to the outfall channel.
Hello everyone. We're going to continue our discussion of diversion headworks. So with some examples, I'll try to explain different aspects of this kind of headworks. Let's first start with the location of this kind of projects. As you can see here, the project that I demonstrated in the previous lecture, it's close to the hilly part or the mountainous part of the terrain. And the reason behind that is that it has a significantly higher elevation in this portion, and that gives it a significantly larger command area. Command area means the area which can be irrigated from this location. And if we construct the diversion headwork much lower than that, suppose somewhere around here, then we would lose the ability to command the portion in the higher elevations, that is here. We can command greater amount of areas by constructing this project even higher up in the river, but that will cause some other problems. As you can see, as we move upstream, the nearby areas become more occupied by mountains. And if we construct a diversion network at this location, then the problem would be to carry the water to these locations, because then we'd have to cross lots of natural barriers. For example, either we'd have to cross these mountains like this, hilly areas, or we'll have to cross these kind of natural drains. As you can see, these natural drains or natural streams or small rivers or tributaries, they are much more common in the mountainous part or the hilly part than they are in the plain part. And that's why if we construct a project in the upstream regions, then although we are having a greater command area, we'll not be able to carry the water through a canal because economically, because it will have to be crossing lots of mountains and natural drains, and that is not a very trivial task, because either you'll have to construct some tunnels, dig some tunnels through these mountains, or you'd have to make some cross drainage works. Cross drainage work means when you are transporting water across a natural stream, that means your canal will have to come from this location to this location, but in between these natural streams will have to be crossed, and that is done by lots of other structures. And therefore, we generally do not prefer this kind of location. And we also do not prefer a location which is much downstream, that is in the plains region, because we will then have very small amount of command area, and these upstream areas, these areas will not be able to command. So this is a kind of optimum region where we can set up our project. There is one problem in this kind of location, is that there are lots of boulders in the river, and that causes lots of seepage through the foundation, because the bouldery state of the river is not, the riverbed is not that, is actually very porous, because it is mostly filled with large particles rather than small silt and sand particles. But we have to compromise at least somewhere. So if in this region we find some place where the amount of boulders is less and it is mostly sand and silt, then that location will be far preferable. Now, I'd like to show you some pictures of this project that I visited a few years ago. So this project is called Bordikarai Irrigation Scheme near Arunachal border. So this is a picture taken from the upstream. Here I was standing on the embankment, the guide bank. So you see the slope of the guide bank is protected with this kind of concrete blocks, and these are the undersluice gates. These undersluice gates will be, these gates are closed so that some amount of water is stored in this location. Here, some other gates are open. You see, these gates are raised so that water can flow through them. And up above, you can see these kind of machines or motors which are connected to these gates by cables. This is one of the divide walls. This is one divide wall, and this is another divide wall. This divide wall is actually part of the fish ladder. This fish ladder is having another wall on the other side, which is not visible from here. And it also has a small gate. That means the fish ladder is not always open. Only when it is needed, then the fish ladder is opened for some time. So up to this point, there are some gates, and there is another additional gate in the fish ladder. The rest of the weir is ungated. As you can see, it's from this location up to this point, the weir is not having any gates, and that means whenever water is above the top of the weir, it can flow through these openings. There are no gates here. And in this particular project, you can see that you cannot see the weir here. These are only the pillars that are supporting the roadway above the weir, but you cannot see any part of the weir because there is so much sedimentation on the upstream that the sediments have risen to the level of the top of the weir. So the weir top or crest is at the same level as the sediments. There is a problem that occurs in most of these kind of projects. And this is the head regulator. This is constructed nearby the undersluices, and here also there are some these kind of arrangements, machine arrangements, and this is a picture from the downstream side. So you can see the downstream of these undersluice gates. So these are the divide walls. This is one, and you can see another one in a distance. And this is a small video that I have taken, and as you can see here, so I was standing on the guide bank or the embankment. This guide bank goes like this to a large distance upstream. And this is the head regulator. There is a small bridge to cross to the other side. Here you see the canal. The canal also, you can see it's not very well maintained, and there is lots of sedimentation. And as you can see, I guess on the left hand side, there is some erosion from the embankments of the canal also. So that has also filled up some portion of the canal. And these are the gates. These are the machine arrangements which are connected with cables, as you can see. And these cables run downwards and they are attached to the gates. So these gates can be raised or lowered as per necessity. Now let's look at some other aspects. I think this model is a little bit more to the scale than the previous lecture. So this is a very wide river, let's say. And this is the fish ladder. This is the weir. This is the one divide wall. Here also, you can consider it a divide wall. And these undersluice gates, the number of these gates or the size of these gates will depend on the highest amount of flood that needs to be released when that flood comes. So here I've only shown 4 gates, but if the highest flood is of very large magnitude, then maybe we would have to provide some more gates here so that when flood comes, we have a larger discharge capacity so that the upstream is not flooded. Now, let's discuss some more about these undersluice, the silt excluders. See, they have a very peculiar arrangement. These are long tunnels. The tunnel very close to this head regulator through which water is transferred to the canal. That is the longest canal, and as we move away, that tunnel, as we move away from that, these tunnels become shorter and shorter. The reason behind that is when water goes into these gateways, they have a component, velocity component like this. And if we have made all these tunnels of same length, then because the velocity is happening this way, then all these tunnels water will not enter these tunnels and they will flow perpendicularly. Once we are making the tunnel, once we are adjusting the tunnel lengths so that this tunnel is the longest and this tunnel is the shortest and so on. So in that case, because the water velocity is in this direction, then a major part of the lower portion of the flow will enter these tunnels, and therefore along with that, sediments or the silt will be trapped inside these tunnels. Sometimes these tunnels may not be necessary if the natural riverbed is much below the sill level. Sill means this level, it is the threshold of this head regulator is called the sill. If the riverbed itself is much lower, suppose 2 or 3 meters lower than this level, then these kind of silt excluders are not needed because the lower part is already much lower than the sill level. So therefore, the sediment which is carried by the lower portion of the current will not be able to enter these gateways. So these are some of the facts that I wanted to add in continuation to the previous lecture. And one more thing that I forgot to mention is that you see these cut-off walls or the sheet piles. These are provided here so that water doesn't simply flow straight from this point to the downstream end of the impervious floor. And because of provision of these kind of cutoffs, they'll have to take a longer path. They have to first go down, then up, then again horizontally, then again in this cutoff they'll have to go down, then up. So it increases the length of flow. But one problem may be that what if the water in the side of the work of this impervious floor, that is on the edges, on the right hand side and left hand side, this water can directly go from here to here. And that can be prevented by extending these cutoffs to a considerable length and inserting them into embankments, so that when water tries to take this sideway, it also has to again go through this longer path, because there will be cut off in the horizontal direction also, and therefore the leakage will be reduced. So that's all for this one. Thank you.